Okay, let's talk related rates. Here we go. We're going to spend some time in section 6A of chapter 5. You may want to pause this video and just read through some of the strategies. People are looking for strategies all the time, and I'm going to go through. You're going to see a lot of these things in action, and just rates are going to be events that are based on time. This is a biggie. Differentiate with respect to time. And we're going to see formulas that don't even have time included in them in our given information, so we're going to be introducing time to be talking about rates. There's lots of things going on here, and this is kind of just meant to be, let's get our feet wet a little bit, and but we're going to be, like I said, we're going to be spending a lot of time in this section, and we're going to take it on, and we're going to be excited about it. It's pretty rewarding problem, some of them. It's really pulling a lot of our strategies or a lot of our calculus abilities, a lot of our mechanics together in some really cool real-world problems. So let's get at it. Example 1, area. The radius and area of a circle are related. We've got this. So area is related to radius with an equation. So write an equation that relates dA dt to dr dt, but we should really think of that as change of A over change of as time changes. How does the area change as time change? How does the radius change in relation to change of time? So dA dt, notice t wasn't even in this, so I'm taking the derivative with respect to t. So we got a little implicit differentiation going on here. So dA dt, the derivative of A with respect to t, well, that's that side, equals the derivative of this, if it was with respect to r, would be 2 pi r. But it's not with respect to r, so that's that little implicit differentiation step that comes in. So this gets added on, dr dt. In other words, the inside derivative, the derivative of r with respect to t, is dr dt. Okay, and that is it. We have related dA dt to dr dt. So that's just very much a warm-up. We got a lot of space for you, but that is all we need for this problem. Okay, multi-step question here. Example 2, which by the way is problem 3 in your book. The radius r, height h, and volume b of a right circular cylinder are related by this. That is the area of the base times the height. That's probably a formula we're going to need to know. How is dV dt related to dH dt? Now we got to read this carefully. If r is constant, alright, this is kind of a new concept for us to think about. R is no longer a variable. If the radius is 5, it is 5 all the time. We know what it is. R is just a number. So we want dV, the change of V with respect to t, dV dt equals, now r is a constant here. So if r is a constant, I've got a constant, r squared would be a constant, times pi, still a constant. I've got a constant times h. Constants survive differentiation, so this is pi r squared. The derivative of h with respect to t, well, if we were taking respect to h, it would just be 1. But then the inside derivative, dH dt. dH dt. Okay, so how is dV dt related to dH dt? Like that. Now, h is constant. I think I'm going to rewrite the original equation, V equals pi h r squared, just to get my constants together. Do you have to do that? You don't have to do that. We'd end up at that point down the road. But I think it's nice. H is a constant, so a constant times a constant is a constant, and constants survive, constant coefficients survive differentiation. So dV dt, pi h, the constant, survives. The derivative of r squared is 2r, but with respect to t, dr dt. That's the inside derivative with respect to t. So we end up with dV, and it's a capital V. Let's get used to annotating with, if it's capital, capital. If You know, if L is written as an L, we're going to write it the way that it's written there. We're not going to introduce our own letters, call it capital L or just a straight line L. We're going to write it the way that it's spoken about. So dv dt is, I guess I would go 2 pi h r h. All of that could be in different orders, but I kind of like the pi and the 2 together, and then we still have a dr dt. Okay, now, how is dv dt related to dr dt if neither are constant? So now we've got a product. I think I'll write this again down here. So my formula was volume is pi r squared h. Now I've got a function of a variable times the function times another variable function. So dv capital V dt is the plain old first pi r squared times derivative of second dh dt plus derivative of first 2 pi r dr dt times the plain old second h. And we really probably should write that as dv dt, and I could have done this along the way, is pi r squared dh dt. It's kind of a common convention to put the dh dt's, dr dt's at the end. So plus 2 pi r h dr dt. Not too bad. Change of r with respect to time, change of height with respect to time, change of volume with respect to time. So at this stage, if I knew what the radius was, and I knew what the height was, and I knew how fast radius and height were changing, I could tell you how fast volume is changing. And that's where we're headed. Okay, well, all I can do is make the derivatives more challenging. If x, y, and z are lengths of the edge of a rectangular box, the common length of the diagonals of the box's diagonal is this. It's sort of like a Pythagorean theorem. In fact, it kind of is. It's also sort of like three-dimensional distance formula. How is ds dt related to dx dt and dy dt and dv dt? So we're introducing t here. I'm going to treat this as though it was x squared plus y squared plus z squared to the 1/2. Just to handle the derivative. So ds dt is outside derivative of, leave the inside the same, reduce, so negative 1/2, times the inside derivative. And I'm taking derivative with respect to t, not x, y, or z. So I get 2x dx dt plus 2y dy dt plus 2z dz dt, and basically I'm done here. So this 1/2, I'm going to distribute that through here, because I don't multiply 1/2 times this and this. In other words, if I have 2 times 3 times 4, I don't multiply 2 times 3 and 4. I just multiply the 3 numbers together in any order. So if I distribute the 1/2 to this, I'm left with an x dx dt plus y dy dt plus z dz dt, all on square root of x squared plus y squared plus z squared. That is ds dt. Okay, so a ton going on there, but you're going to see some real world examples of a box problem similar to that very soon. I am certain of that. The problems that will be very similar to that. Okay, changing voltage. A lot of this is just organization. Changing voltage and current and resistance of an electric circuit like the one shown here. Well, it's not shown, but it's in your book. This is one of the early odd problems. Are related by V equals IR. Suppose V is increasing at a rate of 1 volt per second. And suppose I is increasing. I do believe, it's worth noting, I do believe in your book that this is written as decreasing. Maybe this one's decreasing and this one's increasing, but one of these is decreasing at a rate of 1/3 amp per second. And let T denote time in seconds. Now, I only mention that in case that you're going to go back and you're going to look at answers. So the answers are going to vary from the books. I'm going to treat it just like this. No big deal. What is the value of dV dt? That is the change of voltage as time changes. Well, it says suppose V increases at the rate of 1 volt per second. Oh, it's 1 volt per second. Don't get abbreviation crazy. Don't go V per second when they give it to you as volt per second. They are establishing a convention here for us to use. One thing I'm noting is a lot of kind of labeling challenges when we have answers, when we have quizzes, tests. So if they're asking for volts later on, we're going to end up saying volts. We're not going to go V. We're not going to omit it and just give an answer. We're going to say volts equals. So anyway, 1 volt per second. What is the value of di dt? I is increasing. If it was decreasing, it would be negative. And I think it is decreasing in the book. But it is negative 1/3. Negative 1/3 what? Oh, amps per second. That is our change. They basically gave it to us here. It is increasing. That is our change of I with respect to time. Write an equation that relates dr dt to dv dt and di dt. Now, my approach to this is a little bit different than how the book did it. We have a given equation of volts equals amperes, which is I. Make sure to put the capital I on that so it doesn't somehow become an L or a 1 or something like here, times R. The book just treats it just like it is. Product rules I times R when we're doing this. But when it says relates dr dt to these, I want R isolated. So I'm going to go ahead and make this R equals V on I, and I'm going to quotient rule this guy. So we get dr dt equals low I, derivative high, that is dv dt, I'm capitalizing that V. Low d high minus high d low di dt over the square of the thing below. That relates dr to dv and dt. So I suppose it does if you treat this product rule, but I would think that would be relating voltage. The whole and kind of implies this is related to these together. So I like it that way. I got my dv dt, di dt on the same side, my dr dt on the other. So find the rate at which R is changing. Okay, so I'm looking for dr dt, so I kind of like having that thing alone. They were kind of prepping me for this. I'm not sure why the book didn't do it that way. When V is 12, now that's plain old V. V's not changing at 12. That's plain old V. 12 goes here. I is 2. I goes here. And then we need to find dv dt, maybe find, and I goes here as well. So the rate at which R is changing, dr dt, equals, in place of I, do I have a replacement for I? Yes, I do. 2 times dv dt. Do I have a replacement for dv dt? That is not 12. dv dt is 1. Minus V, volts, 12. di dt. Oh, you know what? I shouldn't have put negative here. This should have been positive. I'll bet you guys realize that. I was still thinking in terms of the book was decreasing, but this is increasing. So back to where we were here. di dt. di dt is 1/3 over I squared. I is 2. 2 squared. In quotient rule, this should always match that. So we get 2 minus 4 on 4. We get negative 2/4 or negative 1/2. Negative 1/2 what? dr. That is ohms. It's our time rate. What time were we dealing in here? Ohms per second. Oh, sorry about that. A little centering issue. All right. Not too bad. It's organizing. It's easy to throw a wrong value in here somewhere, so we're going to take our time. We're going to organize that. They really set us up nicely for this. And what they're really doing is trying to lead us through the whole issue where they may at some point just give us this information along with this information and have none of these other questions there and just ask this last one. Okay, so they're really kind of trying to lead us along the way to get a feel for what we're going to be doing. Okay, let's take a look. Changing dimensions of a rectangle. The length of a rectangle is decreasing at a rate of 2 centimeters per second. The width is increasing at a rate of 2 centimeters per second. So what are they telling us here? They are telling us that dl dt is negative 2. dw d2 is positive 2. They give us a length, they give us a width. Find the rates of change of the area. So I want to find dA. I think I'm going to go capital A. I know that's a lowercase a. I know what I said, but I'm going to go dA. Area is typically a capital A. dt equals. We want that. Well, what is our area? Our area is length times width. So dA dt is the derivative of area. So that is a product rule. So that is first times derivative of second. Derivative of w would be 1, but we have to dw dt it. dw dt, if we were taking with respect to w, it would be 1. Look, that is first times derivative of second plus derivative of first, which is dl dt, times just plain second, which is w. And earlier I mentioned we typically put our dl dt's and dA dt's and dw dt's at the end. Okay, so what do we know? The length of the rectangle is decreasing. They have told me right here, I'm going to jot this down, that dl dt is negative 2 centimeters per second. They've told me that dw dt is increasing at 2 per centimeter. They've told me that L is 12 when W is 5. Find the rates of change of area. So dA dt is L is 12 and dW dt is 2, while W is 5 and dL dt is negative 2. So dA dt at that time is 24 minus 10 is 14. What's our unit measure? We can't miss this. dA, our area would be measured in centimeters squared. Our time unit is seconds. Critical. I don't want to see some random 14 centimeters squared per second just thrown out there in the problem. I don't care if they're only asking one question. When they're asking, find the area, find the rates of change of the area, I want to see dA dt with it. I might be getting a little bit of lag here, so I may stop this before I continue on, but I'll keep an eye on it. Okay, perimeter. What is our perimeter? Well, our perimeter is 2 times length plus 2 times width. Now, I'm going to be really disappointed if our change in perimeter isn't 0, because if the lengths are increasing by or decreasing by 2 while the widths are increasing by 2, they're basically canceling each other off. But let's go ahead and do this. dP dt is, this would be 2 dL dt plus 2 dW dt. Therefore, dP dt is 2 times dL dt is negative 2 plus 2 times dW dt is 2. Negative 4 plus 4, I get d, oh, I didn't want to do that. dP dt is 0. The perimeter would just be centimeters per second. Perimeter is just the length. So there we go. Length of the diagonal. Well, the diagonal, I don't want to call it D. We could go capital D, I suppose. I think I'm going to call it X. Maybe I'd regret that too, but I'm just going to call the diagonal x. So x is the diagonal. If I've got a rectangle, I've got length, I've got width. The diagonal is Pythagorean relation, so that is square root of L squared plus W squared. So dx dt is the outside derivative 1/2 of to the negative 1/2 of the inside function times all of parentheses the inside derivative 2L dL dt plus 2W dW dt. The length of the diagonal, we're finding the rate of change of the length of diagonal of the rectangle. So what do we know here? We have a length of the diagonal, dx dt. Box myself in here. 1/2. The length is 12 when the width is 5 to the negative 1/2. The length is 12. It is changing at a rate of negative 2. While the width is 5, it is changing at a rate of 2. So I'm going to clean this up just a little bit, put this in the denominator, and I get, in the numerator, I get, squeeze this in here, dx dt is 24 negative 48 plus 20 on 2 times square root of, oh, this is going to end up, this is perfect, this is a family. 144 plus 25, 169, so I get dx dt equals, what do I get here? Negative 28 on 2, that's negative 14, the 2 reduces with the 2, all on 13. Dx dt, x is diagonal, it is a length, therefore it is centimeters per second. Which of these quantities are decreasing and which are increasing? Decreasing, let's see, I got an answer of 0, I got an answer of 14, and I got an answer of negative. Therefore, which of these quantities are decreasing? The diagonal. It is negative. Increasing. Increasing would be area. Maybe I should say its rate is increasing, is positive. And might want to mention perimeter's rate is 0, so it is constant. Perimeter is locked in and constant. And not too bad, just a little bit of organizing. And now we actually get a true related rate problem. There's some that are going to be more challenging, but this is kind of a nice warm-up. An airplane is flying at an altitude of 7 miles away and passes directly over a radar antenna. When the plane is 10 miles from the antenna, when S is 10, what is the speed of the plane at that moment? Well, a quick bit of Pythagorean is tempting here. I get 100 minus 49, I get root 51. At one instant, where the plane is right here. And so we are trying to find what is the speed of the plane. We're trying to find this speed right here. So the speed of the plane would be dx dt. That makes sense? So dx dt. What we know is, so that's ultimately what we're looking for. What we know is ds dt is 300 miles per hour. That's what they told us here. So where do we go from there? Well, we do have a Pythagorean relationship that involves this x value. this S value. So I've got, let's do this, I've got x squared plus 7 squared equals S squared. And if I can turn these into, if I can take derivatives and turn these things into things that we can talk about here, then we're going to be in pretty good shape, I believe. So let's go ahead and take the derivative of both sides with respect to time. I get 2x dx dt plus derivative of 49 is 0 equals 2s ds dt. And now I can put in some known values. What am I looking for? I'm really looking for dx dt. So I'm going to go dx dt equals, divide by 2, 2's cancel, I get s ds dt all on x. So dx dt, what it is I'm looking for, equals, at one given instant, s is 10, ds dt is known to be 300 at that instant, and x is root 51 at that instant. So I get 3,000 divided by root 51, I get dx dt is approximately, how do we round in AP Calculus? 420.084. Unless we're asked differently, we round, we either give an exact answer, which could be 3,000 on root 51, or we round to 3 decimal places. What's our unit measure? Well, dx, that is a distance, change of distance, and that is miles, and we are miles per hour, or miles per hour here. Okay, so that is where we're heading. Some of the thinking gets more involved, but that is basically it. We just got to start piecing things together. I really like starting with, hey, what are they asking for? So ultimately, I'm going to end with that. What else? What other information is given? We work without our values in there until we go through the derivative. Without our values, we've come across until we get to a spot where we can substitute those in after we take derivative with respect to time. So there's some strategies. You're going to get comfortable, and one thing I can promise you is you are going to get practice on these. All right? Okay, so you should be fairly well equipped. This is the beginning of our assignment. We've got more to come from this. We also have a big handout of more problems. We're going to get good at related rate problems, or what do they say? You can lead a horse to water, but you can't teach it to drink. Well, if you hold the horse's head underwater long enough, it's either going to learn to drink or it's going to have a problem. So anyway, it's going to end up being enjoyable, I think, if you get into it. They're pretty rewarding. It's kind of cool that we can solve a problem like that, considering where we were, just 3-4 months ago. Okay, there's the assignment, and make sure you're asking questions. You do not want to let this one start snowballing on you.